All right, so far we have a program that can reproduce some of the kinematics we've seen in class, but so far we haven't done anything that we couldn't do with some simple equations that we were already using. So we're going to make this program just a little bit more complex. Before I do that, I would like to add a term here. This is our kinematics equation for the position of the ball. This is the position is the initial position plus velocity times time. You're used to seeing this with another term, and that is 1/2 the acceleration times delta t, the time step, squared. To square, we can't do a caret 2, that doesn't work in Python. We have to do an asterisk asterisk 2, kind of like multiplying it twice. We didn't have that piece in there before, and that was actually okay. When running a code like this with a really small time step, 1/100th of a second is pretty small in these scales, then the fact that the velocity is changing due to acceleration is managed because we're updating it every 1/100th of a second as the loop runs. Now this little piece takes into account the fact that the velocity is changing due to the acceleration over that tiny time step. And so it can give us just a little bit more precision. It can allow us to use a larger time step and still get good results. So we can leave it in there. If we run it, we'll see the same results that we had before. There's not going to be any significant difference in that case. But it's a handy thing to have in for the remainder of this. Now, since we have a program that updates velocity inside the loop all the time, then we can do cases of changing accelerations we weren't able to manage before. So one classic case of changing acceleration is a drag force. I can add a new force right here under the force of gravity. I'm going to add force of drag. And if I remember right, it was 1/2 times a coefficient that represented the shape of the object, the drag coefficient, times the density of air. This was the rho. I'll just write it out as density. Times the cross-sectional area times the velocity, or the velocity squared of the object. That was our equation for drag. We have a couple issues here. One, we can't just square velocity. We can't use a caret. We'd have to use an asterisk asterisk. But also, velocity is a vector in this code. And so when we're talking about squaring the velocity, what we really mean is squaring the magnitude of that vector. To pick out the magnitude, I can use this nice little function, mag_v. You could also do the square root of the sum of the squares of the components, but that takes a lot more to write out and is more computationally intensive. This will give me the right magnitude then. So 1/2 c density times a times b squared, but I do need the drag force itself to be a vector. The direction of the drag force should be opposite the direction of the velocity. So now that I've found its magnitude, I could find its direction by multiplying it by the velocity vector, which already exists. The only problem is now I've got the magnitude of velocity squared here, and then I'm multiplying it by the velocity vector again. What I really want is not the whole velocity vector, but just the direction of the velocity vector, v hat. There's a really nice function in Python that will pick out the direction. It's called norm of v. It normalizes v so it has a magnitude of 1, but still maintains the vector dimension. So now we have a drag force that is this size, 1/2 c times density of the air times cross-sectional area times the velocity squared, and is in a direction opposite the velocity vector. So that's just right. I will need to add that here to find the net force. And since we have that line, we can just plug it right in. The code will calculate the gravitational force, then the drag force, add them together, and use that to find the acceleration, and then continue on its way. If we run this, we're going to have some problems. C is not defined. I know that's not the only issue. There are going to be others. All these things we put in here, we need to make sure the code knows what they are. Velocity is already fine. We have to find that right here. But let's specify the other pieces now. C is a drag coefficient. I recall from an earlier class that for a sphere, it's somewhere around 0.47. We can change that if we decide to use a different object. Density, if we're in air, that's about 1.25 kilograms per cubic meter. Density of air in kilograms per cubic meter. And then the cross-sectional area. We could just put in a value for it, but we do have this object that's a ball, and the ball in the specification here does have a radius already, and we can use that. So we'll use pi r squared. The r is the radius of the ball, ball1 dot radius, And again, we need the caret 2 to square it. So that is the cross-sectional area of the ball. The ball by default has an area of 1. Has a radius of 1. If we want to change that, we can update it in the code here to have a radius of whatever we like. Now if we run the program, it's a very strong drag force. I think our vector there, Susan, is pointing in the direction of the velocity. Let's change that to be the net force. I'm sorry, this is the plot. We'll put Susan in the direction of F net. And you can see how large that drag force is at the start. We could also have Susan be just the drag force or just the gravitational force, or we make a second vector in a different color to represent a different force, whatever we like there. If we were to edit the radius of the ball, we can go right up here and set that attribute. So radius, it's going to be in standard units, which are meters. We started with a default of 1, so I'm going to make it quite a bit smaller. Let's go 0.25 to make it a quarter of a meter. Since we made the radius of the ball smaller, the cross-sectional area will be reduced automatically within the program. So it'll be a quarter of the radius is 1/16 the cross-sectional area, which will give us a drag force that is ultimately 1/16 what it was before. So we should see quite a bit less drag now. Our arrow is gigantic. Let's go back there. Maybe we want not the net force, but just the drag force. And we might need a bit of a scale factor. That looked a bit large. So here's the vector that points in the direction of the drag force, which is always opposite the velocity. So you can go back, you can change anything that you want about this program. We have a very powerful shell right now that will take any forces that you designate that can depend on velocity or position or anything else, find the net force, find the acceleration, and then perform the kinematics. We can draw arrows to represent whatever sort of vector we want in any particular direction, and then we can plot out any components of this motion that we'd like to see. We might, for example, like to see what the drag force looks like as a function of time. I can do that. Remember, f drag is a vector, so I'll need to pick out components of that vector. I'll put the x component of the drag force on the x plot, and I'll put the y component of the drag force on the y plot. And we can see what those look like as a function of time. I see the y drag gets fairly large as the ball comes into a straight downwards fall, whereas the x component starts to trend towards 0 as we lose that horizontal component to the motion.